In this video, we'll continue our discussion of TensorFlow. And so we will continue our discussion of TensorFlow. If you remember, the approach that I mentioned was that to get to deep neural networks, and how to create them in TensorFlow, we were going to take a bit of a long way, right? And we would start at linear regression, right? Because it's so intuitive and it's easy to do in TensorFlow. So that's the previous video. You can see it. That should be here in YouTube. And then now that we've gone through linear regression, now you are ready for the next video, which is logistic regression. Right, so this will be the video that we will use, and then so that's what I'm going to discuss today. We're going to do logistic regression. After we finish this video, logistic regression, then we will start another video which will be neural networks. All right, I know everyone is probably eager to get, I get this a lot from my students, that they want to get to deep learning, you know, and they're like, where's the deep learning? And but actually, by going through linear regression, logistic regression, we'll spend a lot of time on that. But then once you understand those two in TensorFlow, it actually makes understanding neural networks and deep neural networks pretty straightforward. So anyway, so we've completed this part, right? And now currently we are on this one. So this is the topic, so logistic regression. So the learning outcomes, upon completion of this unit, students will have a better understanding of logistic regression. In particular, I will go over a little bit of the theory of logistic regression. You know, I have to do kind of a, you know, since we talked about linear regression, you know, I will kind of start a little bit there where we were, and then we'll make a jump, you know, talk about a few modifications, so let's call them mods, that we will make to linear regression just so that we are ready for logistic regression. All right, so we will look at logistic regression as well, you know, but just basically modify everything that we had here, the functions, add a few other functions so that we can implement logistic regression. And so at the end, you should have enough of a framework to do logistic regression, you know, classification using TensorFlow. Okay, so this lecture is actually probably one of the hardest lectures in the whole series. All right, logistic regression in itself is a classifier that has been around for a very long time. It is, you know, whereas linear regression predicted real valued numbers, logistic regression now predicts the thing that we mostly associate with machine learning, which is classes, 0, 1, 2. Right, so that's the thing that we are looking for. And so, you know, it's definitely very powerful. You can, I think I mentioned in the Weka video that you can actually do logistic regression in Weka and sklearn. You know, it's a non-TensorFlow algorithm, has been around for a long time. However, as it turns out, it can be modeled as a network. Right? And so that's what we're going to learn today, is how that works. And it's very intuitive, and still is a good transition point. So these are the learning outcomes. So, you know, at the end of the logistic regression discussions in labs, the students should be able to write code to implement logistic regression in TensorFlow. Okay. And we'll be using you know, some important data sets for this. You know, most of the classifiers, most of the applications that we do in the labs will involve using logistic regression. You know, it's because we want to compare how logistic regression does versus neural networks versus hidden neural networks. And that gives us usually an incremental improvement as we add a little bit more space for the algorithm to learn. So, the terms here are, basically logistic regression is really itself the one new element of this topic. So this is just, a reminder of what we saw before with linear regression. So in this section of our discussion, we are going to modify and extend our code from the linear regression model so that we can implement, logistic regression, but also one-layer neural networks, which are just the traditional neural networks that have been around for a long time, and even the deeper neural networks that became very popular, after 2012, right? So, so deeper neural networks of multiple layers. And it's going to be, as I said, at least in the TensorFlow code, a very incremental thing where, a lot of the code actually we've already written with linear regression. Now we're just using that same skeleton of code and just making it beefier, adding, more functions, more functionality, etc. So in the following sections, I will make some modifications so that the new models can be implemented easily, right? So that's the objective. Remember, we define placeholders, we define functions, we define, matmul and various elements of TensorFlow. So if you don't remember any of that and you're just looking at this video for the first time, please go back to the, the linear regression and TensorFlow videos. Make sure you're following that sequence correctly, and then all of this should make sense. So here we will use the variables, whereas before we were just calling them x and y underscore, right? And now I'm going to try to follow a more standardized approach or a naming convention. So, I'm going to use whenever I have variables that are directly related to the computational graph in TensorFlow, I will try to add the underscore TF. That stands for TensorFlow. That's just a naming convention, but it should help me to know, oh, this is an element of the graph. So we will use the variable names xtf and ytf for the feature vectors, x, so this is our data, our training data or our testing data, and the labels, the training or testing labels. Additionally, we will use the variables a and b. These we also defined in the previous code. If you remember, these were for the features and the classes. So we will use these variables that we previously described to define the number of neurons per layer. So this, just remember this from the previous discussion or video. In this case, I'll remind you that A represents the number of features in our data set. So for example, the iris data set has 4 features per sample, right? And you remember that. The variable xtf is defined. Remember that TensorFlow gets its name from the fact that it's a computational graph where tensors flow through different points where you have functions, etc. So the variable xtf is defined as a matrix, or if you want to follow the naming convention, a tensor of psi none. Remember that this is a placeholder, so it has n values here for the rows. That's equivalent to the number of samples. And then you have a, right, which should indicate the number of features. So you have that there. So in this case, for the iris data set. Similarly, ytf is defined as none b or none 3. All right, if you remember the 3, here is the number of classes for the iris data set, Setosa, Virginica, versicolor, and none again indicates that it allows n number of samples to be added, which that value can be variable. So you can see the classes there. Now, here, as whenever we deal with classes, so this is new, right? So before, with linear regression, we didn't have to do this because we were predicting real valued numbers. So real valued numbers, right? We were doing that, and so there was no need for calculating, the matching between the classes. But now we are going to do that, so we are kind of introducing here another function, tf argmax. Right, so tf argmax. This is a function that we will be using. I will describe how it works, and hopefully it's very powerful, but it does take a bit of understanding to get used to it. But it is pretty logical overall. So what's going to happen here is we will have at some point in the code to, if you remember when we talk about the four functions for the core functions for deep learning, we said that we had inference. We said we had inference, then we had the loss function, right? Then we have train. And these are the three main ones that we looked at in the linear regression example. And then I did mention that there was a fourth one, something like eval. Oops. Eval or something like that. Evaluation. So there's 1, 2, 3, and then there's this fourth one. So now because we're dealing with classes here, then we have an eval function. And this eval function is the one that needs to take, the real classes, the actual classes, and the predicted classes, right? And it needs to compare them and basically say, what is the accuracy? So what happens is, if you remember, whenever you do inference here, this function, you have something like y, w, x plus b. Right? This y, from now on, you'll see in the code that it's actually named output, or something like that, output. All right, so output will predict a series of classes. So it'll predict, okay, so the predicted classes are, 0, 0, 1. That's what we're used to. However, remember that I did mention before that whenever you're dealing with TensorFlow, the classes have to be one-hot encoded. So that basically means that this is going to be 1, 0, 0, and this is going to be 1, 0, 0, and then this one is 0, 1, 0. All right, so our output, what inference creates, this value output, it's not going to look like this, unfortunately. Instead, it will look like this. It'll be, instead of being a vector, it'll be a matrix. And so that basically means that we have to make some modifications to the code. And so that's why you will see this little function. So output, which comes out to be like this, will have to be passed through a function called the tf argmax. Right? And the tf argmax will just process the data so that, we want it to be like this one, right? We want it to be like that. And so tf.argmax will allow us to take this one as input and sort of convert it into that. All right? So it's, if you think of one-hot encoding as going from here to here, then think of what we're doing now as going from the opposite way, from here to here. Right? So that's, it's very obvious why we're doing it. It just takes, in TensorFlow, kind of a, somewhat, several steps, basically. I wouldn't say complex, but just several steps to do it. So anyway, so it is important to note that you will see this line, yp metrics, and you can see that this variable, I even, is named metrics just to kind of indicate that it has to do with evaluation with this function over here. Basically, we take a TensorFlow argmax function, we're going to pass output. The one here just indicates which dimension we want to argmax through, and then we will convert our data. I will provide an example of this, so it should be more obvious. All right, so we will use this function where 1 is the axis position, right? So we saw this already a little bit when we looked at shape in the previous video, and this is very similar to how shape works. So, and this will be used for performance evaluation purposes. Its use will be shown in the main loop of the code. So that's really where we're going to use it, because that's where we make calls to the functions. YP metrics variable is declared and assigned. So this variable, YP metrics here, we'll declare it, and then it'll be assigned basically the index position of the maximum value. So here it says, so that's kind of the definition of what argmax does, that we declare the YP metrics variable, and this will be assigned the result of argmax. What does argmax do? It takes the index of the max value from output after running it through the argmax function to find the index of the max value, which e.g. is in fact the predicted class. So it's kind of a clever way of getting the results back. So for instance, here's the one-hot encoded version of it. If I want these are the index positions, 0, 1, 2, right? That we know that. So now we want to get a vector representation of it. So what argmax does is it takes the index. So what's the maximum value here? 0. What is the index of the maximum value there? 0. What is the index of the maximum value in the second row? 0. What is the index of the maximum value in the third row? 1. And so on. And so that's all argmax does based on the dimension. Remember that this would be the 0 dimension, and this is the 1 dimension. So that's why we specify this index position here. All right, so now that we have this, we can look at further examples. So the function tf argmax is a TensorFlow function that returns the index of the largest value across the axis, the specified axis of a tensor. So for example, here we have tf argmax of this, vector here. All we have to do is look at the maximum values. So here we have 35, 4, 72, and 2. So obviously that's the maximum value. The index positions are 0, 1, 2, and 3. That means that it returns 2. You can also define an axis like so. So this is a sort of a two-dimensional matrix. So 23, 32, 49, 45, 1, 12, right? So that's what we have. So if we want to return the index position of the maximum values here, so we have 0, 1, and 2. So the maximum value here is 2. The maximum value here is 0. And you can see that 2 and 0. All right, so that's tf argmax. So, a lot of the time, before I explain the TensorFlow, I have to explain all these little tricks that TensorFlow is doing just so that it's easier to read the code. Otherwise, we start reading code and then we see something like this, and we're just not going to know exactly what's going on there. Okay, so keep that in mind. I do recommend, as I said in the book, I have an appendix at the end of the book which has a lot of these functions and examples. So like a little cheat sheet. So you can either create your own cheat sheet or just have the book handy or rip it out or something like that. But there's the good thing about this is there's going to be a fixed set of functions that are used a lot in TensorFlow, and once you have those down, reading the code should become a lot easier. All right, so here is the data, right? So our vector space model data. So you can see here now in the code we have the placeholders x, tf, and y, tf. All right, declared as float, and then remember a and b represent the features, number of labels. Right, so we create this data to store our train and test data. Right, so this is these placeholders. So these placeholders hold that data. And then I just explained what this does, but it has to do with the performance metrics. All right, so for the new models, we continue to use the same functions. So remember, again, I said it's usually in the core functions: inference, loss function, train, And now eval, you can also call it test, just something. These are your own functions. You can give them any name that you want. But these are the main ones. So for the new models, we continue to use the training function, for instance, right? So if you remember, this is the one where we define the learning algorithm, like gradient descent, right? Do you remember that? Right? So if you don't, I recommend, as I said, that you go back to the previous video. So for the new models, we continue to use the training function that we previously defined. Although very little change, it is important to mention that the optimizer and learning rate can be changed. So it is up to you. And in fact, you should play around with the learning rate. Remember that there's several options, functions, but also we set something like this, something like that, something like that, right? So those are usual values that you can try out for the learning rate. You could also change the optimizer. There's something called the atom optimizer. Later on we will see that. It's supposed to be a little bit more efficient. Keep in mind, all these functions in TensorFlow are not just like based on important theoretical frameworks, but they're also optimized. So the code is written in ways that it makes it faster, more efficient to process. So you don't want to use your own defined code here for the most part, but instead you want to use these built-in functions. So there are many alternatives that could be used. And a lot of research has been done on this topic. So this is actually, optimization itself is a huge area of research that has been ongoing for many, many years. And it's still a very much an open area of research for deep learning scientists. So currently it's an ongoing and open research field. Therefore, many optimization approaches do exist, and you can explore them, by searching online. Here in our discussion in the book, we will talk about two basically approaches. And the train function is actually going to be one of the functions we have to modify the least, which is good. Right? So a lot of our work will actually be here in the architecture, here in the cost function, and here in the evaluation, although this one will also become somewhat consistent. So really, this will be our challenge. So if you remember, the inference was y equal mx plus b, right, when we talked about linear regression, and then the loss function was the cost. So for instance, when we were talking about linear regression, we were talking about the sum of the squared errors. Right? So that's what these two things define. So in linear regression, that was pretty obvious. Now in logistic regression, this will change a little bit. This will change a little bit, and then this will also change a little bit. Or this will change completely, actually. So here we can see the training function. We remember that we pass to it cost, and then nothing has changed here. We still define an optimizer. You can still use gradient descent optimizer, whatever learning rate you define in the parameters section. And then we call the optimizer to minimize the cost value. So we minimize this value here. That gives us train up, and then we just return train up. So this basically is our training core function, and very little of it has changed. So in the linear regression, we were training to predict, if you remember, any kind of real valued number. We were training to predict giving square footage, so square feet. We were trying to predict the price, right? And we could predict any price for a house, 200,000, 210,000, anywhere to 290,000, whatever, right? So those were real valued numbers. From this point on, we are going to try to focus mainly on classifiers and predicting classes. So now maybe what we're predicting is, should I buy the house or not? 0, 1, or a -1 and a +1, right? That kind of thing. So those are the kinds of problems that we are going to focus on. The classifiers and so-called also supervised learning class problems, classes. So therefore, in supervised learning, we will usually have the real labels and the predicted labels. So now we have two sets of labels, right? Our models will predict the labels, and we will need ways of comparing them to the real values. So this is where now we will need that fourth equation, or that fourth function. So we will need, so remember, I was saying inference, loss, train, but now we need this fourth one, test, right? And so this is a new function, the fourth one, that we hardly use in the linear regression algorithm, but now it requires a little bit more work. So our models will predict the labels, and we will need ways of comparing them to the real labels. The following function is a way to evaluate the actual or real classes per sample, which, if you remember, they're located in placeholder y_tf, against the predicted classes, which will be in output, right? The only problem, as I said, is that the ones in output, they're one-hot encoded, so we'll need to do a little bit of modification on them. So again, the following function is a way to evaluate the actual or real classes in YTF against the predicted classes in output. Okay, so these against these per sample in the test set. All right, so we compare these two sets of one-hot encoded labels with a new function. So now we have yet another function. This one also is in the appendix, all right, but I will describe how it works. And as the name implies, right? So TF equal, it probably takes a vector of values and compares it against another vector and returns if they are accurate, matching or not. And this is used to measure our accuracy, right? So now what's great about this is that this will be pretty consistent with a function that we defined a few lectures ago when we talked about predicting all the metrics, right? So we created in sklearn actually a function for predicting precision, recall, fmeasure, etc. And so we will use that function again. So this is TF equal, all right? So this is our new TensorFlow function. So TF equal function returns a vector of Boolean values, right? So Boolean values that compares the values in two tensors of equal dimensions, right? So for example, given something like, so we have x and y. So let's imagine we have this. We have x, y, 1, 2, 3, and then over here we have 0, 1, and 3. We can already see that we only have one match. So what TF equal does here is it takes x and y and returns a vector of do they match or not. So the first two do not match, the next line does not match, and the last line does match. So that gives us that, or 0, 0, 1, right? So false, false, true. And so that's what that does, but we will be using this function. So the process will be to take the one-hot encoded vectors, right? The one-hot encoded vectors, 0, 1, 0, like that. And then we're going to convert them into something that looks like this, right? And then once we have that, we're going to use equal to produce that, right? And that's basically the process of how to get, how to evaluate our predicted classes versus our real classes. So you can see now our fourth of the 4 core functions. So these 4 core functions test, or is defined in this next slide. I'm actually calling it evaluate. So this could be either test, right, or evaluate, whatever you want to call it, really. But just keep in mind, it's the 4th function of what we're calling right now the 4 core functions that allows us to measure or compare the predicted labels to the actual labels. So we can see the code here. So evaluate, and then we have 2 inputs. We have YTF, which is the placeholder with the actual data. So let's say the real labels. Let's just keep it simple. Real labels, all right? And then we have the predicted labels. So they're an output. So now what we have to do is we will take argmax. We already defined argmax, right? You remember? We have the one hot encoded, right? Argmax for this dimension, right? Dimension 1, because this is 0 and this is 1. This is output. So it's going to do argmax, which is the maximum, the index of the maximum value. So this will return, if this is 0, 1, and 2, it's going to return that this is a 2. It's going to return that this is a 1, the maximum value. So that's what this does, right? So it creates that. And then we do the same. So we did that with output. And then we do, you notice comma, we do the exact same thing, argmax with YTF. So we do it with both. Same thing. And so now we also had another one hot encoded something there. And then we produce, you know, a vector. So we go from matrix to vector by doing argmax here and argmax here. And then once we have the two vectors, TF dot equal, just imagine you have the vector here and the vector here separated by comma, 2, 1, 2, 0, right? And so TF equal is the function we previously defined, which will just return true, false, or false, false, true. All right, so TF equal then gives us the correct predictions. So now what we have in correct prediction is, you know, like we had before, 0, 0, 1, right? So we have the predicted labels, you know, here, 0, 0, 1, all right? And the next step then is once we have this correct prediction, we take correct prediction casted, which is, you know, just typecasting all the data to be float. And then once we have something as float, we already defined reduced mean in the previous video, so I'm not going to define that one here. I suggest you go back to that video. As I said, create your cheat sheet with examples. But this basically then is a little trick to calculate, you know, like an average of this, right? So, you know, it'll give you, if you do the math, it works out that if you give it a vector like this, it'll say, you know, oh, 33% accuracy or something like that. All right, and so that will give you the accuracy for your, you know, classification. However, we don't always just want to remember, we don't always just want to calculate accuracy. We also want to calculate precision, recall, F measure, etc. And so later on, I'll show you a modified version of this that can do all of that as well. So now we are ready to once again, so now that we understand a lot of those helper functions in TensorFlow, we are ready once again to use our main core function. So as you can see here, now we're going to settle on a specific name for them. So the core functions in TensorFlow, they are inference, loss, training, and now evaluate. So we are ready, 1, 2, 3, 4, so we have a lot of the machinery that we need to make the transition to the logistic regression algorithm. So we are ready to, once again, to use the functions that I just mentioned to define our model. Now, keep in mind, this is where the magic will happen in deep learning, right? So where you define all the elements and where the code will be specific to the algorithm and the architecture being defined. So in our case, since this is logistic regression, remember we talked in our previous example of how, our linear regression model just had 2 layers, 1 output neuron, and actually just 1 input neuron and 1 weight. However, you could have another input neuron, so this would be like if we had x1 and x2. But this was the architecture for linear regression, right? Linear regression. As it turns out now, with logistic regression, the architecture is very similar, but it'll just change a little bit. So now, we'll just imagine we have a 2-class problem, and 2 inputs, for instance. So whereas before in linear regression we had this, now in logistic regression we will add another neuron. And so you can see that there. All right, and that's it. By adding that 1 extra neuron and a little bit of a few tricks, we will be able to arrive at our model. So this is also part of the discussion in this sequence of labs is now, you know, little bit of the theoretical framework to go from a linear regression to the logistic regression. We're only going to look at it intuitively though, but it should be pretty interesting. Since this will, now going back to what the functions, since this will vary based on classifier algorithm, each algorithm will be addressed in its own chapter or in its own set of videos later on. All right, so for now, we just want to do everything until we have a logistic regression algorithm that works. Then we'll do another one. However, this, I always think of this one as the critical part. If you understand this, if you can get through this one, then beyond that, it just starts to become easier, and you can create a deep neural network. So for now, I will simply define how we can call the function. So that's really where I'm starting, kind of where you define the functions, and then we're going to work out the details of all the functions. So now in the next slide, we can see a section on the actual function calls for logistic regression. So here it is. So these are the core functions. And as you can see, these core functions for logistic regression, this section has not really changed, right? So there hasn't, from the linear regression one, we still have inference, we have XTF, A and B, the parameters, we get an output. Remember, this output is equivalent to that Y, and then the output then gets sent with the real. So the predicted and the real are compared in the loss function, because that's usually where an optimization happens. So remember that in linear regression, this was similar to that, right? Y hat. So if you want to think of it in terms of like that, you could say this is Y hat and this is Y. All right, and then the training up just takes cost, plugs it in there, right? And you do the gradient descent algorithm. So this is the thing in the graph that results the node train up. And then finally, once you're done, you want to evaluate the performance metrics. So you're going to take this output, plug it in there, plus the placeholder YTF, which is the same one as this one, right? And compare them basically with the evaluate function that we just defined in our previous slide. Now, if we were defining a deep neural network which with several layers, so remember, currently we are just here, no hidden layers. Right? We're just like there. That's logistic. But if we were defining a deep neural network, the only thing that would change is that this is still that, this is still that, but now in between we have more connectivity, So that is to say, these two, for them to get to this one, whereas before they just go here, right? These lines here. Now for this one to get to here, it has to go through that, and then maybe this one will, go through that, but it can also go through here, and then they can be fully connected or partially connected, and so on. So there's a bit of a longer way to get to our objective, our final neuron, but that's actually a positive thing because, what happens here is that you're giving it more space to learn. Later on, actually in a previous slide or a previous video, I described the intuition of deep learning, right? So I do strongly recommend that you go back to that one. So anyway, but right now we're just specifically looking at the code. So if we were defining a deep neural network with several layers, we can define the same function calls, right? It's just that in some of the functions now, the definitions, the architectures would change. So the important aspect is to keep in mind that the structure of the code is mostly maintained. And we still use the same 4 functions. And that the only thing that really changes is the internal definition of the functions inference, loss, training, and evaluate. A few other things are tweaked here and there, maybe for efficiency, for dealing with the data. But overall, though, we always follow this structure of the 4 core functions and their definition. And in fact, the only 2 functions we change to go from logistic regression to a deep neural network are the inference and the loss. Right? So we don't have to change the other ones. So you can see that here. So this is the core functions if we were defining a deep neural network, for instance, right? So if we were defining a deep neural network, we would do these core functions. So here, notice that it's still the same train function, it's still the same evaluate with the same inputs. The only thing that has changed is, I created a new function. Instead of inference, now I'm calling it inference deep. Instead of loss, I'm calling it loss deep. So I can just replace, in my code, I could still have the original inference and loss for my own reference, but now I create these two new functions with a new definition. So for this one, it would be, let's say, a neural network with two hidden layers. Once we talked about the core functions, we can also talk about the other elements of the code. Like, remember that we've said that, deep neural nets, you create a computational graph, and then we need to define the session and everything like that. So we did that already in the previous code. So in the next set of slides, I'll talk a little bit about that as well. So we still need to use a session and declare it. We still need to initialize. As it turns out, that's exactly as it was before. So that's what's so great about it, right? That once you understand linear regression, a lot of the things carry forward. So this part is the same as what was defined for the linear regression model and is consistent for both logistic regression and neural networks. Earlier in the discussions, I mentioned that one of the advantages of deep neural networks and TensorFlow is that they were designed to process massive amounts of data. All right, so that's really what we're going to, I did a little bit of this in the previous lecture. Now I'm going to do it again, given that, our data eventually will start to get really big, right? So remember that one of the advantages of TensorFlow is that it process massive amounts of data in batches. And so we're going to look at this in code now and see how we can start reading data in batches. So loading millions of records, as you know, directly into RAM memory, would not be suitable for most big data challenges. Instead, to be more efficient, we can load data in batches. That is, we can take our data set and divide it into bins of size, let's say n, and then of n number of samples per bin, right? And so that's, a little bit of the logic that we want to implement here. So here's the initialization and run part. So I talked about that. As you can see, that's still the same. If you remember, basically at this point we would have a computational graph, but it's just like with object-oriented programming, if you want to think of that analogy. It's like a class definition, but there's no instance of it. So you initialize all variables, you allocate space and memory with the dimensions, the data types, etc. Then you define a session, and then you call the session and run in it, right? So you run and initialize the instance, etc. Okay? So this part, pretty much the same as before, so that's great. Nothing to learn new there. Now in the following code section, I will show how we can do the other part that I mentioned, which is reading the data in batches. So reading the data in batches. We need to define the size of each batch, right? So let's call this batch, computation, or batch size calculations. Right, so let's give it a title like that, batch size calculations. So we need to define the size of each batch. In this case, let's say that we want batches of 100 samples each. And the size of the train set file, right? So we want to know how big, how many records the train set file has. So to do that, we will use this function. So as you can see here, I just declared a simple Python variable, number of samples in the train set, right? And I want to figure that out. So if you remember in a previous video, I talked about the shape function in a tensor, right? So in this case, we are saying xtrain normalized. Let's imagine it's the iris data set, right? So it's got 150 samples and 4 features. And so what happens here is the tensor has shape 0 and 1, like that. And so we want to define, okay, what is the size or the shape for index 0? Well, it's pretty obvious here. It's 150. All right, so that tells us that the size, the number of samples in train set is 150. Right? And so we got our value, 150. So that gives us the number of samples in the set, or you could say it another way, which gives us the number of rows in the data set. With these values, we can then calculate the number of batches that we will need, right? So here, number of batches is pretty simple. We take the number of samples divided by the batch size that we define, to be, that we wanted it to be 100. We divide that, so 150, divided by some number. And so now we know the number of batches that we want. All right, so that's a quick way of doing the calculation. And then based on the number of batches, then we can go ahead and now proceed. So here is the code specified a little bit more clearly. So batch size is 100. Here we have X-train normalized shape. We get the number of samples, and then we get the number of batches. Now that we have calculated the batch metrics and we are ready to read the data in batches, remember that we read data in batches so that we can, we don't overwhelm memory. TensorFlow is built for this. So we will use the numBatches variable in the main for loop. Right? So in the main for loop, we will use numBatches here, right, to read the data from the training set. So I will provide an example where, of how we do that. So we're basically going to use slicing. So if you remember, slicing is a topic we've discussed. It's very important. We're going to imagine we have X train like this, and so we're going to follow a for loop logic that allows us to take these number of records with all the features, train the model, then we take the next set, then the next set, and so on. So we're going to perform that in a loop and obtain our data. So in the next slide, you can see a snapshot of the entire main loop. It is included so that there's no confusion about the relation between the parts, and I will describe it shortly. Later on, I will break this up further to describe its different aspects in more detail. Again, notice here that we will use session run. So if you remember in the linear regression code, we actually had 2 for loops, and each for loop had a session. Well, as it turns out, or a session run statement, as it turns out, we only really need 1 for loop, and then I just did that one for academic reasons, just for better understanding by the student. But really, we can do just 1 for loop, but we still need the 2 session runs, because in one session run we run the train op, and then in the other session run we run the eval option or test option. So unlike the linear regression example, here we only have 1 main loop. Well, I guess 2 was not necessary. All right, and I have set this. So here we can see the code, and here's a snapshot of the code, of the code in its entirety. So I'm going to go ahead and explain it. This is the main loop. So basically, remember that before here, all of this included the parameters, the core function definitions, calling the core functions, and initializing the session. So assuming we've already completed those parts, now we are here. This is the start of the main for loop. So the first thing we do is actually, if you notice, the main for loop is actually 2 nested loops. So there's this one and then this one. Right? So we have for I in range n epochs. So that's just the parameter that defines how many epochs we want to run. That is to say, how many times we want to repeat the training process. Right? And so here we have just a simple print statement that prints out the I and the number of epochs. Right? So which iteration of n epochs we are currently under. So this is very useful to keep track of this because it allows us to then later on plot it, right? So for instance, we're going to create a plot, and then at iteration 0, the accuracy is around here, then it's like that, maybe fluctuating. At some point though, it starts to pick up, and then we have a higher accuracy. So, but we'll see how that works in a second. All right, so now to read the batches, which is really the main thing, we have one simple for loop for batch and in range num batches. So num batches is the value that we calculated. All right, and so we're going to grab the first batch. So this is our data set over here, right? And we're going to say, okay, we're going to need a few index positions, for instance. So we have start and end. All right, this allows us to define what is the row index for the first row and for the last row that we want. And so we can do a little bit of math. So if batch size is equal to 0 and we want batches of size 100, for instance, then this would be 0 times 100, right? And so that tells us that, oh, that's 0. And then the n would just be whatever the stat is plus the batch size. So it's 100, so the n is 100. So at that point, we do 0 plus 100, so that's 100, and these are our values. Next iteration, I will be 1. So now batch is 1 times 100, right? So that's going to be 100. So now we are here. Start and end moves. Oops. Start and end moves. So now start is going to be there at 100. Okay. And then since for end is going to be 100, which is start or stop, plus the size of the batch was 100, so that gives us 200. So we grab the next batch from 100 to 200. So this is the one that we slice out of the data, and then we're going to use it. All right, so that's basically it. So a simple little trick. I didn't want to use any like built-in TensorFlow functions or other sklearn functions that abstracted the whole process. You can see it's quite simple to just slice out the data. Really one of the big challenges with machine learning and deep learning is understanding and slicing, right? So this is what that's why I've spent so much time emphasizing this, that you need to understand how to manipulate, NumPy arrays or matrices, these tensors, by slicing the data, modifying the data, etc., to whatever it is that you need. A lot of the time is about getting the dimensions of that matrix to fit the dimensions of the placeholder that you define, or the variable matrix that you define. All right, so now that we have start and end in our for loop, right? So we've got the values for these. Then it's pretty straightforward. You just notice here, that's the next part. We do the session run. Remember, that means that we've defined our graph up here, right? We wrote all the code to define the graph, and now we just want to run the graph. And if you remember from the core functions, trainOp is the function that calls the entire graph. So if I go back to our previous slides where we had these functions, let's go here, right? You can see this is what I'm calling, right? trainOp. Remember, again, I'll remind you here that trainOp is connected, is like a node, and it's connected to cost, right? It's a node connected to cost. Cost is connected to, through the loss definition, is connected to output, and it's connected to YTF, right? And then output is connected to the inference, which is really, if you remember, it's basically this, right? So that's why where the X is XTF, and the B is some parameter that it learns. All right, and so if you remember, this is, whenever we wrote the code of these functions, we've created this simple graph, and then, now we are at the point where we want to call the graph by calling trainOp over here. All right, and so we can run various parts of this, including, assuming, of course, that we've read in the data. So remember that your data from the feed dictionary will have to go in here, right? You have to load it there. You also have to load data in here into YTF. Right? And this is coming from the feed dictionary. So we need to pass that data, and you will see that in a second. So keep in mind, look at this graph here. So feed dictionary will provide data for YTF, feed dictionary will provide data for XTF, and then we call trainOp, and it'll run the entire graph as we have defined it. So if we go back over here, right in the code, you can see that here. So we have session run, we call train up, here it is, and then we provide in the feed dictionary the data for XTF and for YTF, right? And what do we provide to it? Every iteration, we are going to provide X train normalized and Y train one hot. Remember, this is the labels that are one hot encoded, and this is the data that has been normalized. But we don't provide the entire set at once. Instead, we provide it in batches. Notice over here. So we take, remember how it works, right? So we do the slicing by saying start. So I'm doing this one, right, for the X normalized. So we select it from start to end, comma. So that means that from start to end here, right, we are going to slice out these rows. But how do we tell it to get all the columns? Well, we learned in a previous video that all we have to do is provide a colon. So by providing that colon, we're saying, okay, from all the rows from start to end, these, and all the columns. Excuse me. And that way, we can slice out the data from X train normalized, we just say normalized, and plug it into XTF, which is the graph. So we can go back to our graph over here, and that's exactly what we did. Through the feed dictionary, we provided the data into XTF. We do the same from the feed dictionary. We provide the data into YTF, and very much the same way. All right, very much the same way. So here you can see this is the feed dictionary. We do the same over here, start and end for the labels for all columns, and then, but this time it's going to be from Y train one hot. All right, and that's it, right? So we do this. This for loop will basically just train our data over and over and over and over, right? Now, notice that this for loop basically is from here to there, right? And then this is kind of a line over here. So every epoch, we give it a batch. That's what this tells us. Every epoch from this for loop, we give it all the elements in this batch, right? So we take for batch and range of num batches, right? So we take the batches, we train the model, and then once the model is trained, after this for loop executes, then we proceed to the next section, which is to evaluate, right? So now you have a few print statements here, and then we run, this code here. This is what's critical. Right, and so I've explained some of these elements already, but I'll kind of repeat it. So again, same thing. Here's our first session run. Here's our second. So we do session run. All right, notice that before we were just running one element. Now that basically is similar to running one node in the graph. So if I go back to that graph over here, I'm just running this one. Let's say, so I'm going to change the color here. I'm going to change this. I'm going to say I created this, and I'm going to run that one. But I can also, sessions give you the opportunity to run multiple nodes at a time. So you don't just have to run one. So let's say that I want to run this one, but also with the data that's there, I want to run that one. Okay? And so I can do that. I can actually, by creating a little list of pointers to nodes, let's say, I can end up running this graph, but then also this. And so what is output? Remember that output is the inference, right? So you have it defined here. So output is like having the prediction equation, mx plus b. So what happens here is that not only do we load, the train, or actually in this one we're not going to do train, we're going to do eval. So we did cost, loss, and then evaluate is another one. So evaluate is a node, right? And then evaluate is linked to output. But it's also linked to YTF. You see that? And it's really, the node is called eval up. So this is the node that we are going to run now. Eval up, right? So now in that session run, I'm going to end up creating a link to run eval up, but also directly output. So that way I can do whatever eval up wants to do, which is this, evaluate. I'm going to evaluate based on some parameters. But also I want to get, given that test set, I want to get this output. So let's see how that happens. Let's go back to the code here, and you can see, we have session run, but we're going to tell it to run eval op, but also this thing called YP metrics. All right, so I'm doing eval op and YP metrics. So if I go back, there it is. I'm running eval op, this one here, and I said I'm going to run YP metrics. If you remember, I'm not actually running output directly. I'm running this YP metrics, and it's nothing more than, say, a filter. So YP metrics was a node that is linked to output, and it simply just took the whatever's in output, filtered it a little bit, and then you get a better result. So let's see here. So actually our links in that session are to YP metrics and to eval ops. Now let's go back to YP metrics. YP metrics is this one, which is nothing more than output. So there's output, the node that I was talking about. But before, instead of getting output directly, we go and perform an argmax of output, right? An argmax of output. Remember, this is nothing more than, remind you again, we predicted this YP metrics by using, and I explained this already, so I'll do this really quickly. Argmax just will say, okay, the index of the maximum value is 1, 0, 0. So it's a way of taking the matrix form and converting it into a vector form. All right, so that's all that happens. And so that's the graph. And so with the session now, we've added those nodes which allow us to execute additional parts of the computational graph. So now in summary, now it should be more clear. Session run, right, calls eval op and YP metrics, those two nodes. All right, we provide in the feed dictionary X test normalized to XTF and Y test one hot. Remember, this is test now, not to be confused with train. So these are train, these are test, one hot, and they're just assigned to the same placeholders though. Notice that the placeholder is XTF and YTF, and here the placeholders are still XTF and still YTF. That has not changed. So that's just, we do that step, so again, so that in this part here, so whereas this was in the first session, this was feed train, right? And then over here, feed train. Now we do another step where we do, in this next session, the second session, feed test. So we do feed test, and then the same over here. For YTF, we add another node, feed test. And that's it. So that's really, when we do it feed test, it's kind of like we get rid of that one, and we get rid of that one. It gets overwritten, if you will. All right, and so so in that sense, it evaluates whatever is there. So this time around, there's another data set. Conveniently, it so happens to be the test set that I now need to use. Additionally, I should say that in the first session, we ran train op here, but we don't run it in the second session because in the second session, we are running eval op. So we're not training the model again. Instead, we're just evaluating it based on some parameters, and we're also running the inference, which is output, through YP metrics. And now it should be pretty easy and straightforward. So we have, so again, session run, we call eval op and YP metrics. We give it the feed dictionary. We assign all of EX test normalized to XTF and all of Y test one hot to YTF. Once we have this, because we called two nodes, session run will return two values. One is assigned to result, and that's just going to be like your accuracy, and then the other one is assigned to Y result metrics, which is something that we can further use to evaluate the performance of our classifier. So result can be printed out here, and then that just leaves us with these two lines of code here. So if you notice, when we did the sklearn discussion, we learned about this function, print stats metrics. So this function is a function. I've already described it, how it works, etc. So I don't need to do it again. I will simply just say that, this function. So let me just say here that print stats metrics. So print stats metrics takes two vectors, right? Two vectors. And then it evaluates the performance. So it's very similar to say, okay, the real class y_true is 0, 0, 1. The y_result metrics, the predicted is 0, 1, 0, 1. So now remember that we can do all the computations. So these match, these do not match, these match, these match. So we have 75% accuracy. But because print stats metrics was defined with a lot of detail, this is where we get F measure, accuracy, precision, recall, and the confusion matrix. Right? So these are all the performance metrics that we got. All right. So to do that, this item here is just, again, another little TensorFlow thing, quirk. Remember that ytest1hot, this variable here, is a matrix, is a tensor. Right? So ytest1hot is something like 0, 1, 0, 1, 0, 0, 1, 0, 0. So again, argmax, by now you should know, if you've written your cheat sheet, you should have this, or you take it from the back of the book as the appendix, right? Photocopy it or something. You should know argmax returns the index of the maximum value in a matrix given the dimension. So in this case, again, I'll repeat 1, 0, 0, because that's index 0, this is index 1, this is 2, and so these two are in index 0, and this one is in index 1. All right, and that's it. Once we have this, the last part is just for us to perform a little plot. All right, a little plot. So what's going to happen here is, as you're running this, you can store these values. So print stats metrics can be, for instance, be used, or anything else can be used really, to keep track of the accuracy. So every time you print out result, for instance, so this result here could be saved into an array of some kind, or a dictionary where you save the index, I, and the result for every iteration. So once you have that, you have the index for every iteration and the matching accuracy, then you can use plot metric per epoch to print out a nice little plot that shows you. So this would just do something, plot metric per epoch, so it would just show you, okay, and then it starts to pick up like that. So it's good so that we can do that. So in summary, right, we just saw the code. We saw basically that we have a training phase in the main loop, and this section had two nested loops for training, right? The first one is to train the model for n epochs, so we saw that here, right? So this was this one over here, right? That for loop, and then the second for loop is the one for batches, num-batches. So this allowed us to set how many times we want to run the optimization of the model to learn the parameters. Remember that what we're learning in the graph is actually the weights, right? The weight vectors. So to put that into contrast, if I go back to the graph here, right? Remember that these are the parameters. So this M here is another node, which I'm actually going to call W because that's what it should be. So it's W, weight, and B. So these two parameters are the thing that is unknown, right? And we create these graphs so that by doing all of this, we can learn those parameters, and then everything is complete. We optimize to learn the weight vectors. Within this loop, we define a second loop which is for the batch processing, and that's just the big data aspect of all of this. How do we load a lot of data when we have millions and millions of records? How do we load the data in batches? Well, it turns out TensorFlow is built for that. so that and we use the previously calculated variables like num batches. And then we proceed to read the data in smaller data sets. So that takes care of our problem. Just like we did in linear regression, our goal is, to call the train op node with session run, and we saw that, right? And we saw that we can feed it the train set. So we also saw that we assign what is an X train normalize to our node XTF, which remember these are the placeholders, and we assign Y train 1 hot to the, YTF node. The only difference now is that we feed the data in a loop using our predefined batch dimensions. So you saw that. So, we did start and end, sliced out that chunk, then the next chunk, and so on. The dimensions were sta for the starting index and n for the ending index. In the case of X-train normalize, in every iteration, we selected the rows from sta to n by using this and all of the columns. Now, if you notice, I kind of just threw that in there without defining it. This is something that I've already defined in the sklearn videos. And then when we do this in the labs, it'll become very obvious. But basically, when I added a variable with the underscore normalize, it just means that I initially had xtrain, fed it through some scaling function, and then I obtained xtrain normalize. That's really all it means. It doesn't mean anything else. So I took the, the original data and I scaled it, right? And this I've already defined what it is, so I'm not going to do it again. So it only indicates that the data has been scaled, and you can see the previous discussion. The same happens with Y-train. So Y-train, was a matrix, right, or a vector, and then I do one-hot encoding, something like tf.one-hot, right, and that creates my Y-train one-hot. So that's really all that happened there. So they've been converted using one-hot encoding. So that's, basically all of what I said is here. So here's one for loop, another for loop, the start and end, and then the important things, how to use the feed dictionary to fill in the values in these two placeholders, and then we run train on. So the previous loop will train the model and test it at the same time, right? So we saw that in the code. In this way, you'll be able to see how the classification improves as more data is given to the model. So really, if you saw in the code as you were running iterations, every 1,000 iterations or so, you can print a plot. You can look at the performance of the algorithm. And then the final part of the loop, which I also described, focuses on the testing and performance evaluation. Remember that we are now performing logistic regression, and so we have classes. So we have basically something that's classification, and later on we're going to do classification with deep neural networks. So what's important is to remember that from now on, we need to follow this evaluate function of the classes. And you can see the code in the next slide. You can see that here, which I described in detail previously. So session run. Remember that we called two nodes this time, eval op and YP metrics, and we fed it all the test data. Normalize and one-hot encode it. And then finally, we use print stat metrics to get our results. All right? So the previous code section provides the definition of the prediction and testing phase. We called session run for a pair of values, eval op and YP metrics. These two previously defined values are the ones that can evaluate the performance. And so as I described, eval op only provides accuracy, whereas YP metrics allows us to get precision, recall, and F measure. I've already described this, so I'm not going to repeat it. So just how we got, I've said this several times, what ytrue is doing, just takes the one-hot encoded, takes the index of the maximum value of each row, and it creates from a matrix to a vector. Right? And then we just pass these parameters into the print stats metrics so that we can see the statistics just like we've seen in some of the previous labs. The function is pretty much the same. Now there was one new function, which is this one, and I'll just kind of quickly go through it. This is the plotting, so plot function. So this is useful if you want to build your own plots. All right, so visualizing what's going on is always useful. In particular with your deep learning algorithms, you want to see something like this, right? So you want to see the accuracy or something, maybe it's the F measure or the recall per epoch, right? So that basically every iteration, you're keeping track of the little squares here until you can see here around here. So around the 20th iteration, probably 25, the model starts to stabilize. You can argue that by 100, it's really stable. You can see it's almost a straight line there. And so if you want to print these kinds of functions with matplotlib, which is one of the libraries that you can use, you can just do it easily by writing your code. So all that you need is you need to, every iteration, create a list in Python where you keep track of the I. All right, so here x and y just represents what the x-axis and the y-axis will be. So this is epoch, and this is score, whatever you define. So every iteration in this, you put in, iteration 0, iteration 1, iteration 2 in the list, and so on. And over here in the y, you put in the actual score. So as F measure was 0.20. Then F measure was 0.22. Then F measure, for whatever reason, jumped to 0.53, and so on, right? So you keep track of your data. Once you have these two arrays, populated, then you can build the graph. So the way that you do it is actually you assume here that you have this parameter, precision scores list. So this is in the for loop that we were doing. Every iteration, we had to take something like precision scores list, which is an array, and then you just append to it result. Right? You append to it result, and so you were doing that. So you have that assumption. So once you get to this function, then you can reference precision scores list right there. Right? So now we're going to do for I, comma val, which basically means that you're going to take, because this is an array, by doing enumerate, it's like if the value is 0.20 and then this one is 0.30, in the first iteration, if I write I and val here, so these. So when you do that, it's just going to say, oh, this is 0 and it was 0.20. Then the next one, oh, that's 1 and 0.30, and so on. Right? So that's what enumerate does in Python. And so we do for I, comma val, and enumerate for precision scores list, which is my array of precision scores. I'm going to iterate through that whole thing. And then in these two that I created, in this one and this one, which represent these axes here, right, I'm going to just append the value. So for x epochs, I append the index. For y epochs, I append the actual value. Once we have those there, that's the first part, that's the data part, and this is the plot part. So this one's pretty straightforward in plotting in matplotlib. We assume here that we've created, import. We've done something like import plot as PLT or something like that from matplotlib. So once we have that object, then we can create a scatter plot, which for it, all we need to do is provide the data for the x-axis and the y-axis, which we provide here. They're obviously aligned in that sense, so we can just plot them. And then you specify some parameters about, what you want to have in your graph. So as you can see in the graph has, it's green, it's little squares, so it's squares and they're green of a specific size. And then we have the title here is like score per epoch. We have a little grid over here, and then we have these labels over here, right? And a legend over here, right? And so we have all that information, and so we define all of that here. once we have collected our data in x epochs and y epochs, then we can do a scatter plot with x epochs, y epochs, right? And then just define that we're using like squares, light green of specific size. The label is score, and then in the x label and y label we define epoch and score, a title that we want to show a legend for what everything means, show in a grid, and then the final, if you don't run this command, nothing will appear. You need to do plot show. So you build a plot and then you show it. And that's it. In summary, the final part of the code, plot metric per epoch is used to plot the metric value every 1,000 epochs. So we stored the metric values in a list such as this one, and then proceed to plot these values using the very powerful matplot library. There's a lot that you can do with this library, a lot. I'm not actually going to cover much of it in this course. I'm sure there's a lot of tutorials out there on YouTube or online that you can use on how to create very nice plots, but it's a very powerful library for sure. And then, as I said, the output then just looks like this graph over here. And this is very nice because, you know, it gives you a picture of how your algorithm is doing and, you know, how long it's taking to train your with your data. So in summary, we actually started discussion of the transition from linear regression to logistic regression. So to keep the videos, you make the video a bit shorter. We're going to stop here in this video, and then the next video will now start with the logistic regression theory. We're going to talk about that, and you know, how do we actually build the actual architecture. So if you notice, you know, we talked about how to read the data in batches. So batches, right? We talked about that. We talked about the evaluate function, right? So we focus really our attention on these simple things. But if you remember, you know, as far as the core functions, inference, loss function, train, evaluate. So these four core functions, we really did not talk about these because these have to do with architecture and optimization. All right, so these will be the focus in the next video. And instead, in our discussion today, we talked about evaluate, right? We talked about how to take the predicted classes that we will have now and how to, do all the calculations, all the slicing, and then to evaluate the metrics. We also talked about the for loops. So we did the for loops here, all right? We talked about doing in epochs and then doing this in batches, right? So we talked about that code and everything that follows there. So that's basically the summary of our discussion in this section, which is really just how to transition from linear regression to logistic regression in TensorFlow. In the next video, we will talk about logistic regression.